All right, let's get started. Hola, good morning, everyone. Buenos dias. Thank you all for coming. I'm very happy to see so much interest in our work. Introductions, my name is Vinay, and I've worked with FutureWave for over a year now in the Seattle Research Center. Besides leading this effort here, I work with container networking and container runtimes over there. And unfortunately, my co-speaker, Peng Du, could not be here today because of unforeseen events last week. But he did a great job helping me with this project. So what are we going to talk about today? We are going to go over a customer scenario which motivated this whole effort for us. And we're going to quickly take a look at the scaling in Kubernetes today and how pod scheduling works, because this is needed for the design. And we're going to go a little bit deeper into our solution, our design for the vertical scaling of Kubernetes pods. We'll look at some of the policy controls that we implemented as part of this effort, and how we do the failure handling when we do the vertical scaling. Then we're going to look at how we could potentially integrate with the vertical pod autoscaler, which is a project that was created to automate the process of scaling your pods for you. Nobody's going to sit there and do this manually. So, and then we had another issue we had to look at, which is how to handle memory spikes. We're going to go over that. And then I'm going to cross my fingers and do a demo, and we'll do Q&A after that. So this is a biotech industry customer, and they are currently using Kubernetes jobs for running their applications. This is a very long process. What I understand is that the end-to-end run for an analysis takes almost a day, and they have some jobs which run for almost 4 hours. So if your pod were to get killed or restarted because of resources, they lose a lot of work. Now, they have this legacy applications, and they could potentially rewrite it to, become more restart resilient, but that's not a priority or not feasible for them to do. It's don't fix if it ain't broken kind of motto there. And so they were looking to get this feature where they estimate this elastic pod feature would save them about 50 to 60% in resource utilization cost savings, which otherwise they're resizing for peak usage, and they're not utilizing the full capacity of the cluster nodes. Besides that, this has been a very long desired feature. The first issue requesting this feature was raised 4 years ago, so it's been a while. Horizontal scaling, as many of you already know, it's the bigger the load, more number of pods you need. Smaller the load, you reduce the pods. Kubernetes supports this already. And vertical scaling, this is going to be the focus of our talk today. This is where we increase or decrease the resources given to a pod that's in, for now, it is CPU and memory for our talk. And this is common for stateful applications and the job that I just described with our customer scenario. Vertical pod autoscaler can do this for you, but the way it does it today, it evicts the current pod and writes the new resources, which is restarting the pod. And that may not work for our customer. The scheduling, this is a very high level overview of how a pod gets scheduled. So we have the core components, the API server, scheduler, kubelet, and the runtime. I left out etcd intentionally for space. So it starts with a pod create. We put the pod in the API server, and the scheduler, which is watching for new pods, its job is to find pods that don't have a node and find it a home, which is a node. And to do that, it runs through a bunch of predicates and priorities. It's a non-trivial process. It takes a little bit of work to do that. And one particular predicate that's of interest to us here is called pod fits resources. This predicate filters out the nodes which can accommodate the pod. And once the scheduler has found a node for the pod, it executes a bind operation, and the pod is assigned to the node. It essentially sets the node name for the scheduler in the pod spec. Now the kubelet goes to work. The kubelet is watching pods that are bound to its node, and when it sees a new pod come to its node, it does a pod admission control check. It does another check to see if the pod's going to fit on the node. This is necessary because Kubernetes supports multiple schedulers, as you may know, and that inherently brings in a potential race condition. So your kubelet is the ultimate gate. It gets to say yes or no. So let's assume everything goes well. Then the kubelet now moves to set up the pod, which is today it sets up the C groups, and then it calls the container CRI API, asking the runtime to start the container. And the container runtime does that and reports back status. And kubelet then updates the pod status saying, okay, container is ready, container is running, init everything. And let's go to, when we started working on this project, we were faced with a couple of potential options. The choices we had, first choice was to directly update the pod resources and let the kubelet and the scheduler update their data in parallel. So one thing I forgot to mention earlier, the scheduler, it keeps a cache of the node available resources. It does this for performance reasons, I suppose, and because of that, it doesn't have a live view of the node available resources. And if we went with this option, let's say the kubelet were to apply the resize. It says, okay, yeah, this capacity request from the pod, I can do that, I have a capacity. But at that very moment, the scheduler might be working on assigning a new pod to this node, which is going to use that capacity. So when that new pod arrives at the node, it's going to get rejected, and then the scheduler will have to go back to work all over again from the top. So this would increase the overall scheduling load for the system. So the other option was to put the resize into the workflow, bringing the scheduler into the decision making just as it would if it were a new pod coming in. We looked at this as, okay, the current pod has requested X, now it's requesting X plus Y, so it's as if it's a new delta pod of size Y on the same node. So we went with this option, the scheduler. The way we do this is we set an annotation saying, I want, my resources are X, I want Y. And scheduler looks at this and looks at its node available resources cache and says, okay, looks like the node has capacity, I'm going to let this through. And once the scheduler lets this through, it does so by updating the resources section. The kubelet takes over and it does this admission check. So we are focused on updating the resources section here, as shown in the spec. So going a bit more deeper into this, it starts with the API caller, which you could be using kubectl patch if you were doing it manually. In automation, it would be a vertical pod autoscaler, which would be doing this for you. So in our case, the customer wanted jobs, so naturally we started with the job controller, but this could be done for any kind of controller, or it could be done for a pod, standalone pod. And so what we do is we patch the job, saying, okay, I have one CPU, I need two. And then the API server does some basic validation, which is you should not change the K8s class by doing this. And once it sees that the request is good, there is no errors there, it updates the etcd and updates the job spec. Now, the job controller here is watching the job spec. It sees there is a difference between the job spec and what the running pod has. And it says, okay, this is a case of a resize. We need to bring the running pod to the desired size that's in the job spec. So it sets the annotation, and the scheduler, which is watching the annotation, goes to work here. So what the scheduler does, it interprets that annotation as a resize request, and it checks its node resources cache. If there is capacity, it will say, okay, we're going to go to step 6, which is update the pod resources. Now, if the request cannot be filled in that node, then it looks at the policy. If the policy allows, okay, if I can't get 2 CPUs on this node, put me on some other node, then it will evict the pod and then reschedule it to a new node. If the policy says, no, don't reschedule me, then it will mark it as failed. So in this case, we're going to go with step 6, where we had the capacity and we're able to update the pod resources. Now it's kubelet's time to act. So kubelet is watching the pod as well. So it sees that there is a update to the pod spec, and it says, okay, looks like it needs more resources or less resources, and it runs through the same predicates that the scheduler is looking through, same algorithm. So it says if it fits. This is again with the multiple scheduler race condition in mind. So assuming that it fits, then it will set the resize pod condition to true. If it does not fit, it would set the resize pod condition to false. Now, and again, if it doesn't fit, it will check policy and evict if necessary or mark as failed. Now we go to the next step, where if the scheduler is watching the pod status once the kubelet has had a chance to update this, look at the resize request and update the pod status. If the kubelet was able to successfully resize the pod, accept the updated request, then there is nothing else left to do for the scheduler. This is a completion of a successful resize operation. However, if the kubelet said, no, I couldn't take this resize because there's no capacity, then the pod resize condition would be set to false, and the scheduler will roll back the resource update that it did in step 6. And at this point, the job controller will come and take a look at it and say, oh, this is not, they don't match. I'm going to try, but this is a failure. I'm going to come back later and try again when I might be more successful. So we got requests for a certain degree of control from the users, and we came up with these policies. The in-place preferred policy, this is where you say, okay, if I cannot be resized to the requested capacity on that node, reschedule to a new node, and then I'll be fine. This is, in this case, you could have, this is for when you have deployments, this would be the kind of scenario that you would look into. There is a thing called pod disruption budget, where you specify, okay, I want 5 pods, but at any given time, I want 2 pods to be online. So in that case, the scheduler won't resize all 5 pods at the same time. It's going to look at, oh, okay, there is a PDB. I'm going to have to, I can reschedule 3 pods, but I'm going to keep 2 of them for later. So it marks them as failed, and the controller comes back later and says, okay, this was marked as failed, and then it's going to retry later. So eventually, the resize request will get to the desired state. And in place only, that's the kind of policy that our customer would potentially use. They don't want, if the CPU, if you're starved for CPU, and you can potentially continue running suboptimally. So you'd say, okay, I'll take my chances. I'm going to continue to run here because rescheduling me is more expensive. And the customer whose application doesn't want to be rescheduled would choose this policy, and then Kubernetes system would try to get to that at a later point through retries. Restart, this is an interesting one where there are some applications where even if you were to successfully resize the pod on the same node, it's not able to use that. This one example that I have for this is Java with the XMX flag, where you specify the max limit. Even if you increased it, you have to restart the application to get that, make use of that increased memory limit. And failure handling, this came out naturally as we were working through our design. We figured that Kubernetes does, it's common for Kubernetes to retry with a back off. Okay, I'll try now. If it doesn't work, I'll try 2 seconds later, 4 seconds later. We figured we could also do this based on events. So if you have a policy of in-place preferred and you failed because of pod disruption budget, when you get the notification that your PDB is available, you try. That's a good time to try. And if it is the case where in place only and you don't have resources on the node, then when other pods of the same priority are higher, they leave the node. That's a good time to try. So we would do this based on events, besides, in addition to doing based on time. Vertical pod autoscaler, this integration with the VPA, we were looking into how to do this because eventually we will be using VPA. What we did here was, this is a very brief overview of how VPA works. Here you have the recommender, you have the pod VPA object where the recommendations are written, and you have the updater which takes actions. So VPA, the way it comes up with recommendation, it reads the current pod usage of resources from the metrics API. I believe API server has this metrics API, which pulls it from a metrics server. You have to run that component. And then you have Prometheus, kind of a time series database, which stores the historic utilization of the pod. And VPA consumes these two pieces of information, and the recommender comes up with a recommendation. In this case, if you look at the example there, we have 2 CPU and 1 gig of memory. Maybe VPA says, okay, you might benefit with more memory, so I'm going to write 2 gig of memory with 1.5 lower bound, 2.5 upper bound. This is a very abbreviated example of what a recommendation looks like. And once VPA recommender has written the recommendation to the VPA object for that pod, VPA updater goes to work. VPA updater is watching the pod VPA object, and its job is to figure out how to give this pod the new recommended resources. Now today it does this by evicting the current pod, and then the controller creates a new pod to replace that, saying, oh, I'm missing a pod. So it's going to create a new pod, and during admission control it rewrites the resources section with the new recommended resources. With our work, that is unnecessary. We just simply update it, and which is essentially, we call the patch API to do that. Coming to memory usage spikes. So even with this feature, you could have your pods getting out of memory killed. This can happen for a few reasons. You have there is a certain sampling interval from the metrics API, which is, I believe, 30 seconds. And VPA response, there is a lag with VPA as well. So if your memory is really spiking, which happens at the start of the application or maybe at the tail end, you could potentially have your app killed before the VPA has had a chance to resize it. So we looked into this, and we were looking for a solution. We looked at this kill disable flag that's there with the C group, and I believe it's kind of supported with different runtimes, although it's hit or miss. We put an annotation there, which the kill disable annotation, which if you would set to true, we disable the killer for the pod. And what happens in this case, your pod won't get killed if it exceeds the memory limit that you were asked for. Instead, the applications in the pod get suspended, they're paused, and then until VPA has had a chance to look at the usage and then update, give it more memory, for example. And once that happens, the application becomes runnable again, and it's resumed, starts running. Again, this is suitable for our customers' long-running jobs, where if you're a 4-hour job at 3 hours 50 minutes, you hit this condition, you do not want to be killed for that. And with that, let's do the demo. In this demo, what I'm going to do is I'm going to run this kubectl patch command, where I'm patching the container named stress. I'm patching its resources. So it currently has 2 CPUs and 1 gig. I'm going to be patching it to 2 gig. So hopefully it works. If you're in the back and you can't really see it clearly, please feel free to come forward. And I apologize, the text is going to be a little small for the people who are at the back. So this is the job that I've been talking about. We are looking at this job would run a pod contains one container named Stress. It's your Ubuntu image with Stress app installed on it because I want to run some stress tests on this to stress the memory. And it's going to ask for 3 CPUs and 1 gig of memory. So let's create the pod. So it looks like it's created, and we're going to go in and just watch the pod. Now, this is just your standard kubectl describe pod output. I put some filters in there to filter out information that we really don't care about and focus on what we are interested in here. So you can see, as you can see, the pod has been scheduled. It's running on node 1. It's got this container ID here, and it's got 3 CPUs and 1 gig of memory. Now, let's run the stress application asking for 500 meg. What this does is it gets into the container, execs into the container, and runs the stress tool and asks for 500 meg of memory and runs for 5 seconds. Exit status 0, which is a good thing. We were successfully able to run the stress tool. Now, what would happen if we were to go above the limit? Oops. Well, it's expected. You have 1 gig of memory and you're going for 1.5, and the ohm killer says no. So signal 9 is you got terminated. Today, VPA would potentially do this, fix it, would take care of this for you by analyzing what your current usage is. It's growing and then giving you more memory. But as I mentioned earlier, you have to reschedule the pod. You have to evict the current pod and then update the resources of the new pod. Let's try doing it without updating the resources. So I'm gonna have a handy little script that does it for me. So all this does is runs that kubectl patch command that I described in the earlier slide. So we did that, and if you're watching the blue window, you see that it's gone to 2 gig. So the pod is running, the container is running, it hasn't been restarted. Let's make sure that's the case. So we just run this again and see. It's now gonna go and allocate 1.5 gig. It seems to be getting farther along down the road, and exit status 0. That's a good thing. All right, now I can uncross my fingers, and let's continue. So we had, just a second. So late last year, as we were finishing up the first iteration of this project, JD.com's, one of JD.com's engineers reached out to us, and they said they were interested in trying out our work. And we partnered with them. They needed enable this for deployment pods. So we worked with them and got it working for deployment, and they're reporting that it's doing fairly well, and it's in pre-production staging. They found another use case for this where if they see pods that are not scheduled, they're pending because resources is not available, they do a walkthrough and see which pods are not using the resources that they've been given, and then try to resize them down, and that way that they get these pending pods running. So they get more work done. And the last slide that I have here, these are the resources. It's the design doc and implementation. These are pretty much legacy at this point. What I want to focus on is the third bullet point over there. Based there was another design proposal that was preceding us. So with Carol and Beata from the auto-scaling team, they started this new proposal, which merges the two designs, and then it's work in progress at this point. I highly recommend that you guys go to this GitHub Kubernetes enhancements link and take a look at that if this interests you. Before we conclude, I have a few asks. Container runtime gurus, if you're in the audience, please ensure good support for update container resources API and consider ohmkill disable. We kind of would like that feature to be enabled and work well across different runtimes, Kata especially. And we have been working closely with SIG-Node on this new KEP, and one of the things that we could use help with, SIG-Node could use help with is reviewing code, PRs, and looking at issues. If you have the bandwidth and the interest, we'd really like you to do that. There is another talk right after this talk by Carol and Beata. It's going to talk about this latest KEP and where things are. I highly recommend that you attend that. So with that, I conclude the presentation and open up for questions. I have the mic here.
Let's say I have a long-running job, let's say 2 hours, 3 hours, and I don't want to deal with defining the resources all the time, like enlarging my CPU or whatever. Do you recommend using the VPA or like dealing with it manually? Like, let's say the job fails, let's raise the memory, and maybe it will fail again, maybe not. Like,
okay.
What do you recommend? Especially when I'm talking about a new job, something I didn't test it yet.
Okay, the question is, do you recommend manually updating the resources or using VPA? I believe the answer is to use VPA. Nobody wants to. You could do it manually for experimenting to see what is the right size for your resources, but VPA has a mode where it lets you do that. For more details, I think I would recommend looking at the VPA project documentation. I would not do this manually. I would use the VPA recommender to come up with recommendations and set that as your starting point and let VPA use when this feature comes in and becomes available upstream. I would recommend using that.
Okay, and one more question. Like when you define the VPA, you can choose what update mode. Like you can do off, initial, auto, whatever. Like.
Yeah, currently they have those modes of initial and auto. The auto mode, I believe, will...
auto mode, like it runs your pod and it creates it like automatically if it sees like it like... that's what I'm asking. Like
the auto mode is the one where it would update it for you. Today it does it by evicting. I would say that eventually it should become, instead of evicting, updated in place. But if not, there might be a new mode for it. I don't know where that will land. This proposal is still in a work in progress, and once it's approved, we'll work on implementing it, and then it will land. It'll take some time for that. Okay. Any more? Do you have a question? Pardon me? I'll address this question.
In your use case, you had this very important job that you could not kill, but if there are not resources on the nodes, can you also evict other pods to other nodes? Because I think there are also other initiatives to make the scheduler more dynamic, to spread the workloads even, and how does it work together with the proposal that you had now?
Yes, in the new proposal, we are considering that. So the scheduler looks at any pods that are of lower priority than the current pod, and it evicts them as part of giving it more resources. That's natural. If you were to schedule a new pod, it would do that. And if a new pod with a higher priority comes in, it does the eviction anyways. That feature came in recently, I believe. I don't know, maybe in the last year or so. So that feature is there. It's going to leverage that. Do you have a question? Anybody?
So just one question. How does it handle extended resources, or does it handle them at all?
Today, we don't have support for extended resources. Mainly VPA does not support it today, but that's something that's been asked before. If there is a strong desire for doing this for extended resources, the support will eventually come in. The scope of this is kept for the CPU and memory at this point, and potentially ephemeral disk space.
Are you considering also scaling down in memory or CPU usage based on, for example, Prometheus measurements?
Yes. Yes, in the new cap, we are going to be auto-scaling down. The auto-scaling down of memory is a little bit of a challenge because you can't really take away memory if the pages are in use. So we're still working through how we could really do that. I think the solution there is to set your limit at slightly below what's being currently used and try to force a reclaim. That is what it would do at this point. But CPU, we can take away. Giving and taking away CPU is pretty easy. We do that. That's, I think it works. I haven't really tested this end-to-end, but you can see that the CPU count has been reduced and the C group enforces that when you do that down. Back there.
Just one question. So is this also integrated with horizontal cluster autoscaler? If the cluster is run out of resources, does VPA also trigger bring up to like more nodes?
The last I looked, it was not recommended to use VPA and horizontal scaling together. I don't know if the support for that will come in at some point. I might be a little bit out of date on my information, but at this point I believe it's not supported. Anybody? All right, it looks like we can conclude this talk or wrap up.